Hello students, my name is Mr. Abiy Anteneh. Welcome to Mathematics Unit 3, Grade 11, Solution of Systems of Linear Equation. In this unit or in this lesson, we'll try to cover these ideas. One, augmented matrix. What is augmented matrix of a system of linear equation? And also elementary row operations, which are very important in solving a system of linear equations. And finally, solutions to a system of linear equation using Gauss elimination method. So, a system of linear equation that can be represented in a matrix form as AX equals to B, where A is a coefficient matrix, X is a column matrix of variables, and B is a column vector of constants. To apply row operations, we construct augmented matrix, coefficient matrix with a column vector or a column matrix of B, which combines coefficient matrix A with constant matrix B. So what is augmented matrix of the following system of linear equation? So augmented matrix is a matrix which is obtained by a coefficient matrix and a column matrix B. So what is a coefficient matrix? So coefficient matrix of this system of linear equation is, what are coefficients of X for the first equation? It's 1. And coefficient of X for the next, it's also 1. Coefficient of X, it's 1. So the first column represents coefficients of X for each equation. Then coefficients of Y, 2, 5, and 0. Because on the third equation there is no variable Y. And also the third column will contain a coefficients of Z. That is -3, 1, and -6. So augmented matrix is a matrix which contains coefficient matrix with a column matrix B. Column matrix B is, that is 1, -3, 0. So this matrix is what we call augmented matrix. So in solving a systems of linear equation, only we need this augmented matrix. So what are elementary row operations? To solve a system of linear equations, we need these elementary row operations. There are 3 basic types of elementary row operations. The first one, row swapping. Swapping meaning interchanging any 2 rows. Ri will interchange it with Rj. We can interchange any 2 rows of augmented matrix in solving a given systems of linear equation. Then the second one, row scaling. We can multiply any row with non-zero constant k. Ri will be changed by k times Ri, where k different from 0. So this elementary row operation is what we call row rescaling. We can rescale, we can multiply by any non-zero constant, any row. Then the third one, pivoting, which is Ri will be changed by Ri plus k times Rj, adding a multiple of one row to another row. This operation helps us in reducing a system of linear equations to simpler form for easier solution extraction, meaning to determine the solution will use these 3 basic elementary row operations: rescaling, pivoting, and swapping. So to solve a system of linear equations, there are different techniques, but it's better to use Gauss elimination method. A Gauss elimination method is a method of solving a system of linear equation which is written in matrix form AX equals to B by reducing AB, which is augmented matrix, into row echelon form using elementary row operations. You know what is row echelon form. So using Gauss elimination method, meaning reduce augmented matrix into row echelon form, or it can be solved by reducing given augmented matrix into upper triangular matrix. So we'll try to apply row operations to solve a system of linear equations by Gauss elimination method. Now we have this example: solve a system of linear equation, this by applying elementary row operations. So to solve this, we need only augmented matrix. So what is augmented matrix of this? Augmented matrix of this, 1, 2, 1, then a coefficients of y, 1, 1, minus 3, and the coefficients of z, 2, 3, 1, and a column matrix B, that's 1, 2, 0. Now we'll apply elementary row operation to change this augmented matrix into row echelon form or to upper triangular matrix. So always, if the first entry for the first column is 1, that's good. If it is not, either we have to rescale or interchange any two rows. For example, row 1 and row 3 have the same leading entry, which is 1, so we can interchange. Then after we interchange, every terms below the first leading entry, that's 2 and 1 must be zeros. So how we can make these two constants 0? So we have to use pivoting. So R2 will be changed by R2 minus twice of R1. We'll only focus this value, 2 minus what constant times 1 will be 0, that's 2. And also, this must be equal to 0, it's 1. So the first entry is 1, so R3 must be changed by R3 minus row 1. Now this is an elementary row operation, what we call pivoting. So write the first row as it is, then 2 minus twice of 1, that is 0. 1 minus twice of 1, that's minus 1. 3 minus twice of 2, it's also minus 1. 2 minus twice of 1, that is 0. Then for the third row, 1 minus 1, that is 0. Minus 3 minus 1, it's minus 4. 1 minus 2, it's minus 1. And 0 minus 1 is minus 1. Good. Now we have these two terms or entry 0. The next, we'll try to make this value 0 by applying pivoting. Either pivoting, we can rescale. We'll apply any of elementary row operation. Now let's make the second row leading entry 1. So row 2 will be changed by minus 1 times row 2. So it will be changed to 1, 1, 2, 1, 0. We'll multiply by negative 1, 1, 0. Third row we'll write as it is, 0, minus 1, minus 1, 1. Then to change into row echelon form, this 4 must be 0. So to make this 4 0, use immediately the above row. So R3 must be changed by R3 plus 4 times row 2. So we have to write row 1 and row 2 as it is. So let's copy first 1 is 1, 2, 1. And the second row, 0, 1, 1, 0. Then the third row, minus 4 plus 4 times 1, that is 0. This is 0. Minus 1 plus 4 times 1, minus 1 plus 4, that is 3. And 1 plus 4 times 0, it's 1. This can be enough, but to reduce into row echelon form, this 3 must be 1, so we can rescale, but it's not important. Now after this, we can use backward substitution. This augmented matrix represents a system of linear equation. That's we can write x plus y plus 2z equals to 1. Y plus z equals to 0. The last one, 3z equals to 1. So, 3z equals to 1. So, z equals to 1 over 3. So, we have this value from the last row. And also the second row states that y plus z. We have a value of z, that's 1 over 3, which is equal to 0. So y equals to minus 1 over 3. Good. Similarly, to determine the value of x, the first row stated that then having the value of y and z to find the value of x, the first equation is x plus y, that's minus 1 over 3, minus 1 over 3 plus twice of z, that's 2 times z, 2 over 3 equals to 1. This implies x equals to minus 1 over 3 plus 2 over 3 is 1 over 3. So that is 1 minus 1 over 3. This implies x equals to 2 over 3. So the solution set is the set containing x, that is 2 over 3, comma, minus 1 over 3, comma, 1 over 3. So we can write the solution set is 2 over 3, comma, minus 1 over 3, then comma 1 over 3. Now if we have such solutions, this system of linear equation has a unique solution. A unique solution implies unique value for x, y, and z. In the same way, let's do another examples. Example 3, solve this system of linear equation. So we'll follow the same technique as we have seen on the above slide. So to solve a system of linear equation by reducing into augmented matrix, into row echelon form, or into upper triangular matrix, let's write the augmented matrix. So augmented matrix of this, it's 2, 1, 3, 3, minus 2, 1, then a constant or coefficients of z, minus 1, 3, 2, and the column matrix B is a matrix that is 5, minus 1, 4. Now look this augmented matrix. So to change into row echelon form, the first leading entry must be 1. So either we have to rescale, either we have to divide the first row by 2, or it's better to swap this, swapping, interchanging row 2 and row 1. So we can write row 1 will be changed by row 2. So we can write the first row as 1 minus 2, 3 minus 1, and the second row will be 2, 3 minus 1, 5. And the third row as it is 3, 1, 2, 4. So this is augmented matrix. So we'll reduce this augmented matrix to row echelon form. So these 2 must be 0 and 3 must be zeros. So what must be? Row 2 must be replaced by row 2 minus twice of row 1. And row 3 must be replaced by row 3 minus 3 times row 1, because only we'll focus on the leading entries. 2 minus what constant times first row must be 0, that's 2. 3 minus what constant times row 1 must be 0, that's 3. Now we write the first row as it is, 1 minus 2, 3 minus 1. And then the second row, 2 minus twice of 1, that is 0. 3 minus twice of minus 2, that's plus 4, it is 7. Minus 1 minus twice of 3, that is minus 7. 5 minus twice of minus 2, that's plus 2, so it is also 7. Here 3 minus 3 times 1, it is 0. 1 minus 3 times minus 2, that is plus 6, so it will be 7. 2 minus 3 times 3, that's 9, so 2 minus 9, it's minus 7. Here 4 minus 3 times minus 1, that's 4 plus 3, it is 7. Now we have this reduced matrix. Now let's apply rescaling. Let's divide the second row by 7. So we can write like this. Row 2 will be replaced by row 2 over 7. Now let's see what will happen. That's 1 minus 2, 3 minus 1. And if we divide every interest of the second row by 7, so the equivalent row is 0, 1, minus 1, that's 1. The third row as it is 0, 7, minus 7, then 7. And also the next row operation, this constant 7 must be 0, because our objective is still to reduce this one into row echelon form. So to make this 0, use immediately the above row. So 7 minus what will be equal to 0. That's 7 minus 7 times row 2. So we'll make row 3 as row 3 minus 7 times row 2. So we'll copy first and second rows as it is. 1 minus 2, 3 minus 1. And the second row, that is 0, 1 minus 1, and 1. 7 minus 7 times 1, that is 0. Here already it is 1 before. Minus 7 minus of 7 times minus 1. That's minus 7 plus 7. It is also 0. 7 minus 7 times 1. This is also 0. When we reduce augmented matrix into row echelon form, if the last row of reduced echelon form is zeros, this system of linear equation has infinitely many solutions, because it is 0 times z equals to z. So for any z, this equation holds true. So let z equals to some constant t, where t is an element of real number. So if we let z equals to t, we can solve y and x in terms of t. So The second row states that y minus z, that is z is already t because we denote it by t, equals to 1. So what is y in terms of t? Y equals to t plus 1. Good. And similarly, the first row, that's x minus 2y plus z equals to minus 1. That is x minus ty of y. We have a value of y, that's t plus 1. So ty of this value is 2t minus 2 plus 3z. That is plus 3t equals to minus 1. So let's solve x in terms of t now. Good. When we take t to the right hand side, it will be minus t. And we have here minus 2. So minus 2, then plus 2. That's minus 1 plus 2 is plus 1. Now we have the value of x, a value of y, and z in terms of t. Therefore, how we can put the solution set for this, a system of linear equation? It is the set containing what is x minus t plus 1. What is y in terms of t? It is t plus 1. And what is z? It is t. For t is an element of real number. So such types of a system of linear equation has infinitely many solutions, because if we take any t, the values of x and y depends on the constant t, so we'll have so many solutions to such types of a system of linear equations. And also, before listing the final answer, when you have such types of reduced matrix form, if we look, the second and the third row is equivalent. So if you have such equivalent rows, you can generalize this system of linear equation has infinitely many solutions. Then to write in terms of t or in terms of t, x, y, you have to reduce into this form. Example 4, solve this system of linear equation. So the procedure, the way is the same, but the final answer may be different from the examples that we have seen on the above slides. So similarly, let's put augmented matrix and we'll reduce that augmented matrix into echelon form by applying row operations. So look now, 1 minus 2 minus 4, 1. This is the first row. Then the second row, minus 1, 1, 2, 0. The third row, 3, minus 3, minus 6, 2. Now the first entry of first row is 1, so it's good. So using this augmented matrix, our objective is to make minus 1, 0, and 3, 0. So what row operations must be done here? R2 must be replaced by R2 plus R1, because our objective is to make this number minus 1, 0. So minus 1 plus 1 is 0, that's our objective. Then on row 3, to make this 3, 0, row 3 will be replaced by row 3 minus 3 times row 1. 3 times row 1, because 3 minus 3 times 1 is 0. Now let's copy the first row, 1, minus 2, minus 4, and 1. Then the second row, minus 1 plus 1, it is 0. 1 plus minus 2, it's minus 1. So the third entry, 2 plus minus 4, that is minus 2. 0 plus 1, it's 1. And also for the third row, 3 minus 3 times 1, that is 0, minus 3 minus 3 times minus 2, that is minus 3 plus 6, that is positive 3, and minus 6 minus 3 times minus 4, that is minus 6 plus 12, 86, and 2 minus 3 times 1, that's 2 minus 3, it's minus 1. Now to change into row echelon form, the leading entry of the second row must be 1. So let's multiply the second row by minus 1. So R2 will be replaced by minus R2. The other rows will copy as it is. So the first row, 1, minus 2, minus 4, 1. The second row, 0, 1, 2, minus 1. Because already we rescale by multiplying with minus 1. Then 0, 3, 6, and minus 1. Next, we'll make these 3 equals to 0. So what operations must be done here? Row 3 must be changed by row 3 minus, we'll use immediately the above row. That is 3 times row 2. Because 3 minus 3 times 1 is 0. Now let's copy the first 2 rows as it is. 1, minus 2, minus 4, 1, 0, 1, 2, and minus 1. Here the first entry is 0. 3 minus 3 times 1, it is 0. And the other entry, 6 minus 3 times 2. That's 6 minus 6. It's also 0. Then finally, minus 1 minus of 3 times 1. That's minus 1 plus 3. So that is equal to 2. Now the reduced augmented matrix is representation of a given system of linear equation. What implies here x minus 2y minus 4z equals to 1. Here y plus 2z equals to minus 1. Then finally 0x, 0y, 0z equals to 2. That is 0 times z equals to 2. This is the information that we can obtain from the last row. So 0 times any number cannot be equals to 2, which implies there is no a number z that can make this equation true. So what we can generalize now, this system of linear equation has no solution. Therefore, a solution set is the set containing empty set. So there are exercises for you. What is augmented matrix for a system of linear equation? You know what is augmented matrix? It is a matrix with a coefficient matrix and a column matrix B. The other one, solve this system of linear equation, convert augmented matrix into echelon form or into upper triangular matrix. Then finally you will have these values for x, y, and z, which implies this system of linear equation has a unique solution. And also, what is the solution set of the following system of linear equation? Here, use augmented matrix and reduce into row echelon form. After you reduce into row echelon form, the answer is minus 3k plus 4, comma, k minus 3, comma, k, for k an element of real number. Meaning it is expressed in terms of k, which implies this system of linear equation has infinitely many solutions, which describes, if you remember from the above slide, when we reduce augmented matrix into row echelon form, you will have 0 rows at the bottom. Then example 4, solve this system of linear equation, use the same technique. Then finally, this system of linear equation has no solution. That's empty set. So in this lesson, we'll try to cover elementary row operations, system of linear equation, or simply to find a system of linear equation. This method is particularly useful for solving a large systems of linear equation and determining a system has either unique solution, infinite, or no solution set. This is all about the lesson. See you next time. Bye.